So is everything made of vibrating strings? That's a simple question with a very, very complicated answer. The short version is, maybe. The long version is a story about the biggest problems in physics and one of the most beautiful and frustrating ideas anyone has ever had. Let's start with what we know, or what we think we know. For a long time, we've pictured the basic building blocks of the universe as tiny little points, dots. An electron is a dot, a quark is a dot, a photon, the particle of light is a dot. They don't have any internal parts, they have no size, they are just pH points. This idea has worked incredibly well. It's the foundation of something called the Standard Model of particle physics, and the Standard Model is probably the most successful scientific theory in human history. It describes three of the four fundamental forces of nature: electromagnetism, the strong nuclear force which holds atomic nuclei together, and the weak nuclear force which governs radioactive decay. It has predicted the existence of particles with stunning accuracy. We find them in our giant particle colliders, exactly where the theory says they should be. It's a triumph, but there's a problem, a huge one. The Standard Model completely leaves out the fourth force, the most familiar one, gravity. The best theory of gravity we have is Albert Einstein's general relativity. And general relativity is also a triumph. It describes gravity not as a force, but as a curvature of space-time itself. Massive objects like the sun warp the fabric of space-time around them, and planets like Earth follow those curves. That's what we feel is gravity. This theory predicts black holes, gravitational waves, and the expansion of the universe. And we found all of those things. It works perfectly for big things: stars, galaxies, the whole universe. So we have two amazing theories, one for the very small quantum mechanics and the Standard Model, and one for the very big general relativity. Here's a disaster: they don't work together at all. They are written in different mathematical languages, and they are based on fundamentally different ideas about reality. Quantum mechanics is all about probabilities and discrete chunks of energy, a jittery, uncertain world. General relativity is about smooth, continuous, predictable space-time. When you try to combine them, the math breaks. It just completely falls apart. Try to describe gravity on a very small scale, like at the center of a black hole or at the moment of the Big Bang. These are places that are both incredibly massive, needing general relativity, and incredibly tiny, needing quantum mechanics. When you try to use equations, they spit out nonsense. They give you answers like infinity. An infinite amount of energy, or an infinite density. When you get infinity as an answer in physics, it's not a deep statement about the universe. It's the universe's way of screaming at you that your theory is wrong. This is the biggest problem in fundamental physics. The clash between our two best theories of reality. We need a new theory, a deeper theory, a theory of everything that can unite the world of the small with the world of the big. The theory of quantum gravity. This is where the strings come in. The idea didn't start as a theory of everything. It started by accident back in the 1960s. Physicists were trying to understand the strong nuclear force, the one that glues protons and neutrons together. The math was a mess. But then a young physicist named Gabriele Veneziano found a strange old math equation that, by sheer luck, seemed to describe the behavior of these particles perfectly. It was just a guess that happened to work, but nobody knew why. Later, other physicists figured it out. The math that Veneziano had found was the math that described a tiny, vibrating, one-dimensional string. It was a wild thought. What if these particles weren't points at all? What if they were little loops or snippets of string? The idea didn't work out for the strong force. We found a better theory for that involving those point-like quarks. So, string theory was mostly abandoned. It was a curious dead end, but a few physicists kept thinking about it. They started to look at the properties of these hypothetical strings, and they found something incredible. And a string isn't like a point. A point can just move around, but a string can do something else. It can wiggle. It can vibrate. Think of a guitar string. When you pluck it, it vibrates. And depending on how it vibrates, it produces different musical notes. A low note is a slow vibration. A high note is a fast vibration. You get a whole range of different sounds from the same single string just by changing its vibration. String theory says the universe works the same way. The fundamental entities of reality aren't points. They are unimaginably tiny, one-dimensional strings of energy. They are so small that if an atom were magnified to the size of our solar system, a string would be the size of a tree. To all our experiments, they look exactly like points. We can't see their shape, but they're not points. And just like a guitar string, they can vibrate. Here's the core idea. Every different vibration, every different note a string can play appears to us as a different kind of particle. One specific pattern of vibration makes the string look like an electron. It has the mass of an electron, the charge of an electron. It is an electron. Change the vibration, pluck the string a different way. Now it has the properties of a photon, the particle of light. It has no mass, no charge. It is a photon, vibrated another way, and it's a quark. Another way, and it's a neutrino. Everything we see in the universe, every particle of matter, every particle of force is just a different vibrational mode of the same underlying entity, a string. This is an incredible simplification of the world. We no longer need a whole zoo of different fundamental point particles. We just need one thing, the string. The universe is a cosmic symphony. All the rich diversity of particles and forces we see is just the music being played by these fundamental strings. This idea is elegant. It's beautiful, but does it solve the big problem, the clash between quantum mechanics and general relativity? This is where string theory produced its first miracle. As physicists were studying the math of these strings, they looked at all the possible ways a string could vibrate. They found vibrations that corresponded to electrons, photons, quarks, all the familiar particles of the standard model. But then they found one they hadn't been looking for. It was a very specific vibration of a closed loop of string. It described a particle with zero mass and a specific amount of spin. When they calculated its properties, they were stunned. The properties of this particle were exactly the properties that a hypothetical particle of gravity, the graviton, must have. No other theory had ever predicted the graviton. In other theories, you just had to put gravity in by hand. You had to assume a graviton existed. String theory didn't just make room for gravity. It demanded it. Gravity, in the form of the graviton, was an inevitable consequence of the theory. A theory that started as an attempt to describe nuclear forces had, completely on its own, produced the particle of gravity. This was a huge moment. For the first time, there was a theory that naturally included both quantum mechanics, the different particles, as vibrations, and general relativity, the graviton. It seemed to effortlessly bridge the gap between the two worlds. So how does it solve the problem of the infinities? The problem with point particles is that they are infinitely small. You can get infinitely close to them, and so forces like gravity can become infinitely strong. This is what breaks the math. Strings are different. They aren't points, they have a tiny, tiny size. They are smeared out. You can't get infinitely close to a single point on a string because the string itself is always wiggling. This smearing out is just enough to smooth over the infinities that plague the old theories. When you calculate interactions in string theory, you don't get crazy answers like infinity. You get finite sensible numbers. This all sounds amazing. It sounds like the problem is solved. The universe is made of strings. But, as with any big idea, there's a catch. And with string theory, there are several very big catches. The first one is weird. The math of string theory does not work in the universe we know. It doesn't work in 3 dimensions of space length, width, height, and 1 of time. The equations break down. They only become mathematically consistent in a universe with more dimensions. A lot more. The original versions of string theory required 26 dimensions. Newer, more advanced versions, which we'll get to, require 10 dimensions of space and 1 of time, for a total of 11 space-time dimensions. So where are they? We very clearly experience only 3 spatial dimensions. If I want to meet you for coffee, I only need 3 pieces of information: a street, a cross street, and a floor number. That's it. Where are the other 7 dimensions of space? String theorists have an ingenious, though very strange, answer. The extra dimensions are compactified. They are curled up on themselves on a scale so tiny that we can't see them. There's a classic analogy to help picture this. Imagine a garden hose stretched out across a long distance. From far away, it looks like a one-dimensional line. An ant walking along it can only go forward or backward. That's its entire universe, one dimension. But if you get very close to the hose, you see that at every point on that line, there's also a tiny little circle. The ant can walk forward and backward along the length, but it can also walk around the circumference of the hose. Up close, the hose has 2 dimensions, the long one, and the tiny, curled up one. String theory suggests that our universe is like that. At every single point in our familiar 3-dimensional space, there exists a tiny, complex, curled-up shape in 7 extra dimensions. These shapes are called Calabi-Yau manifolds, and their geometry is incredibly complicated. They are so small, far, far smaller than an atom, that we have never been able to detect them. We move through the 3 big dimensions, completely unaware of the tiny, curled-up dimensions all around us and within us. This might sound like science fiction, and in a way it is. It's a speculative idea that comes straight from the mathematics. It's not something anyone saw or measured, it's a requirement of the theory. If the theory is right, these dimensions must exist. But the fact that we can't see them makes the theory very hard to test. That's not the only catch. Another one is called supersymmetry. In the process of making string theory work, theorists found they needed to introduce a new kind of symmetry into the universe. This symmetry proposes that every fundamental particle we know has a heavier, undiscovered superpartner. For every matter, particle, like an electron or a quark, there is a corresponding force particle, a selectron, or a squark. For every force particle, like a photon, there is a corresponding matter particle, a photino. This idea, called supersymmetry, or SUSY for short, is quite elegant. It helps solve some other problems in physics, and it's a key ingredient in making string theory stable. If string theory is correct, these supersymmetric particles must exist, so physicists went looking for them. The Large Hadron Collider LHC at CERN, the most powerful particle accelerator ever built, was partly designed to find these particles. The idea was to smash protons together at incredibly high energies and see if any of these heavier superpartners popped into existence for a fraction of a second. And the result? Nothing. Absolutely nothing. Despite years of searching, we have found zero evidence for supersymmetry. Not a single superpartner. This is a big problem. It doesn't kill string theory because it's possible the superpartners are just too heavy for even the LHC to create. But it was a major prediction, and the fact that it hasn't panned out has made many physicists very skeptical. The problems don't stop there. In the 1990s, it turned out there wasn't just one string theory. There were five different mathematically consistent versions of string theory. This was a mess. A theory of everything shouldn't come in 5 different flavors. Then came another breakthrough. A physicist named Edward Witten showed that these 5 different string theories were actually just 5 different ways of looking at the same thing. They were all connected. They were all part of a single, deeper, more mysterious theory that he called M theory. The M theory lives in 11 space-time dimensions. Nobody knows what the M in M theory stands for. Witten himself has said it could be magic, mystery, or membrane. The last one is important because M theory isn't just a theory of strings. It also includes other objects called branes, short for membranes. These can be 2-dimensional surfaces, 3-dimensional blobs, or even higher dimensional objects. In this picture, our entire universe could be a 3-dimensional brane floating in a higher dimensional space. This was another huge step, but it came with its own gigantic problem. M theory is not a finished theory. We don't have the actual equations for it. All we have are approximations that work in different situations. It's like having a few pages from the middle of a book, but not the cover, the table of contents, or the first and last chapters. We have a glimpse of a beautiful structure, but we don't know what the whole thing is. And this leads to what might be the biggest, most philosophical problem of all. Remember those extra dimensions that have to be curled up. It turns out there isn't just one way to curl them up. The mathematics of string theory allows for an enormous number of different ways to do it. The number is staggeringly large. It's estimated to be something like 10 to the power of 500. That's a 1 followed by 500 zeros. Each of these different ways of curling up the extra dimensions would result in a different universe. A universe with different physical laws, different fundamental constants, a different number of particles. Our universe, with its specific laws and constants that allow stars and planets and people to exist, would be just one possible outcome among a practically infinite number of others. This is called the string theory landscape, and it's a deeply troubling idea for many physicists. If the theory allows for 10 raised to the power of 500 different possible universes, and we just happen to live in one of them, how can we ever test the theory? How can you prove it's right? Any set of physical laws we measure could potentially be found somewhere in that vast landscape of possibilities. A theory that predicts everything predicts nothing. This has led to a fierce debate. Critics of string theory say it has become a branch of philosophy, not science. Science is supposed to make testable predictions. If a theory is so flexible that it can't be proven wrong, even in principle, is it really a scientific theory? They argue that after decades of work by thousands of brilliant people, string theory has not produced a single prediction that we can go out and test in an experiment. The extra dimensions are too small to see. The superpartners haven't shown up. The strings themselves are too tiny to ever detect directly. So why do people still work on it? Why do so many of the world's best physicists dedicate their lives to this idea? Because despite all the problems, it's still the best candidate we have for a theory of everything. There is no other theory that comes close to describing both quantum mechanics and gravity in a single consistent mathematical framework. The way it solves the infinity problem and the way it naturally predicts gravity are still incredibly compelling. For many, it feels like it has to be right. The mathematics is too beautiful and powerful to be just a coincidence. Even if string theory turns out not to be the final theory of the universe, it has been incredibly useful. The deep mathematical ideas developed for string theory have found surprising applications in other areas of physics and even in pure mathematics. It has given us new ways to think about the universe, new tools to solve problems. It has been a powerful engine for discovery, even if its ultimate destination is unknown. So let's go back to the original question. Is everything made of vibrating strings? The honest answer is, we don't know, and we may not know for a very long time. String theory is not a proven fact. It's a hypothesis. It's a work in progress. It's a vast and complex mathematical structure that might, or might not, be a description of reality. It offers a beautiful and unified picture of the cosmos, where everything from a beam of light to a black hole is part of the same cosmic music. But it asks us to accept some very strange things, like hidden dimensions and a landscape of possible universes, with no experimental evidence to guide us. Science isn't about having all the answers. It's about asking questions and following the clues wherever they lead. String theory is one of those paths. It's a path that has taken us deep into a weird and wonderful mathematical world that might lie just beneath the surface of our own. It might be a dead end, or it might be the path that finally leads us to a true understanding of the fundamental nature of everything. For now, the idea that you, me, the stars, and the empty space between them are all made of the same tiny vibrating strings is just that, an idea. A powerful, controversial, and profoundly beautiful idea. The music of the strings might be playing all around us, but for now we can't quite hear it. We can only imagine what it sounds like.